Good morning, afternoon, or evening, depending on what time you're watching this episode, and welcome back to Constellation Crew. I'm super excited for this episode because we're going to be talking about some stuff that I have been dying to talk about since I was 10. Very complex stuff, but I promise it'll be really easy in this episode. We're going to start with the basics first. But we have a new crew member again. I would like to introduce to you all Dr. John Millis.
Hello, thank you for having me.
Thank you for coming. This is very exciting. I'm really excited for this episode. So, of course, as always, when we have a new crew member, we like to ask a couple of questions. But for a brief introduction, Dr. John Millis works here at Ball State University and is the head of the department at the Physics Astronomy office. And you do research with high energy astronomy and astrophysics, right? And deep sky objects?
Yeah, so specifically, I primarily work with an instrument called Veritas, the Very Energetic Radiation Imaging Telescope Array System. For you future scientists, if you want government funding, come up with a snazzy name. And we basically use these telescopes in southern Arizona to study some of the most extreme environments in the universe. Supernova explosions, massive black holes that are consuming galaxies from the inside out. And we look for gamma rays coming from these sources so that we can try to understand the physics of what's happening.
Wow, crazy stuff. That's the stuff that drew me in as a kid. I had no idea what any of the TV shows and radio shows were talking about, but I knew it was cool. Well, now I sort of do, because me and Kyree are currently taking some astrophysics classes with Dr. Bob Barrington, which is actually kind of fun. So we sort of have a gist of what's going on. So why are you here today? Or why are you here at Ball State?
Yeah, so a couple of reasons. Number one, I just have a passion for helping to educate young people and talking about science and specifically physics and astronomy. And Ball State is a wonderful place to do that because we're very focused on student education and really mentoring undergraduate and graduate students. But we also have an interest in research, and we have the opportunity to get students involved in that. And that's something I'm really passionate about. And I'm here because we're talking about some of my favorite types of things in the universe. We're talking about some pretty extreme objects, some supernova remnants, and even an active galaxy. And that just gets me really excited.
Awesome. All right, one final question before we move on. So what got you into high energy astrophysics specifically?
That's a great question. So when I was an undergraduate, I ended up taking a course in stellar astrophysics, and I sort of began to figure out that I really liked astrophysics as a field. I'd always liked astronomy in the night sky, but I was never really great about, doing star walks or, being able to point out constellations. But I liked learning about the objects in the universe itself. And so when I got to graduate school, I kind of thought maybe I wanted to do something in astrophysics, but I was also interested in particle physics and really trying to understand how fundamental particles interact in extreme environments. And so I thought maybe I wanted to do that. And I happened to kind of stumble upon this area of high energy astrophysics. And I didn't really know what that meant, but in kind of a simple way, it kind of bridges the gap between astronomy and astrophysics and particle physics. We look at these extreme environments where particles are accelerated to extremely high energies, and then they interact in complex ways with hot gas, magnetic fields, and even extreme gravitational fields near black holes. And these interactions cause them to radiate, and we can measure that. And it seemed like a really great way to blend my two primary areas of interest in physics, the astrophysics and looking at sort of the really interesting, cool objects in the universe, but also really kind of trying to study some of the fundamental particles that we know exist and how they interact.
Wow. A lot of that is kind of what we're talking about in Dr. Barrington's class as well. And it is very, very intriguing, just the thought that a star can excite gas around it, make it change colors and stuff. It's very fascinating. And it coincides with your background with the Aurora Borealis.
Exactly.
So thank you, John. I appreciate our little brief interview. So we're going to start with our program today. We're going to be talking about some high-energy astrophysics objects, and some of these objects are in constellations we've covered before, but we'll still go over some brief specifications about each constellation that we visit. So right now we're in Stellarium, or Stellarium, depending on how you want to pronounce it, facing about south-ish, southwest, just after sunset, and I think we had, I don't want to say daylight savings because it's spring forward, right? So that's not daylight savings. It's spring forward. It's something. We had to change our clocks. So now it's brighter outside when it gets close to the evening. Usually when we leave astrophysics, it's really dark out, and now the sun's still out. Thank goodness. I appreciate that. But for our first object, we're going to have to go north. So I'm going to spin Stellarium a little bit. Lucky for us, we're not in the dome. Sometimes people get dizzy in the dome when we spin. Cool. So, now we have to find a good old friend of ours. We visited this constellation before in our Valentine's Day episode. If you were there for that or have seen our episode before, we're going to look for Cassiopeia. So we're facing north, and if you watched our episode, we talked about how Cassiopeia can appear as different shapes. Sometimes it's a 3, sometimes it's an M or a W, or a backwards 3, a backwards E. I always mess up the fourth and final one. But the point is that it's different shapes in the sky because it is a circumpolar constellation. So does anyone see a 3, an M, a W in the sky?
I actually do.
Okay, So what general direction should I go?
You should go a tad bit more towards the northwest.
Okay, so our north is down here for our viewers.
The north is down there, and the northwest would be a bit to your left. And then if you keep on going up diagonally, you can see that blurry. Yep.
There we go. I believe that's how you write a 3. No, it's not. I think that's how you write an
That's
E.
probably an E, and I'm probably mixing up. Yep.
Listen, I don't know how to spell. I don't write very well. Just, me and English, not very good. But it's okay. We're learning. That's what we're here for. So here's our good old friend Cassiopeia. And I decided to put the borders up today for constellations because I feel that sometimes we forget about those kinds of things. Kind of like when I was really little, I thought the solar system ended at Pluto. Not at all true. I thought the constellations ended when you connected your dots. Once the lines were done, that was your constellation, that's where it ended, but that's not the case. These red faint lines here, if our viewers can see them, are the boundaries of the constellation. So anything that's within this red line counts as a part of Cassiopeia. But I believe Kyree has an interesting object in Cassiopeia today, and I'm going to try to bring up the search bar for that.
Yes.
So what do we have?
Well, you go ahead and pull that up. The object that we're actually looking at is called Cassiopeia A, and typically the best way to find that is by, I can't remember which end it is, unfortunately, but on one of the ends of Cassiopeia, that would be the star within that constellation called Beta. And essentially, we give each stars within a constellation a Greek letter to signify how bright they are in the context of that constellation. So the brightest would be Alpha, and then would go down from there. Beta will be the second brightest, and Beta is on one of the ends for Cassiopeia. For Cassiopeia. Near that is what we're looking at right now, Cassiopeia A, which is, I believe, a supernova remnant. So essentially, a star that has unfortunately lived throughout its lifetime and has exploded, and this is what's left of it now. Cassiopeia A is about, I want to say, 11,000 light years away from us. And if we put that in miles, so that way we can have an easier way of understanding that, it's 64 quadrillion miles away, which, again, doesn't sound like a fun road trip. I've already made this joke before with trillions, and now we're going up one, so I think I'll pass on this one.
There's not enough beef jerky for that trip. Not enough beef jerky in the world for that trip. No, thank you.
But yes, Cassiopeia A is a supernova remnant that was first discovered at around 1947 by Martin Ryle and Francis Graham Smith. it was a discrete astronomical radio source, which is essentially a type of light. So as we know, we have the visible light. There are different, essentially frequencies and wavelengths of light. Essentially, if you imagine light as a graph, it would make this little wave, and then the wave can be shorter or longer, so on and so forth. And essentially, radio is, I believe, a shorter form. And
I thought it was a longer form. Because
I may be forgetting about it. Yep, it might be a longer form. Yep, because I'm thinking, yep.
Yeah, because the radio telescopes are those giant dishes. They're really, really big because we got to catch the long wavelengths. Okay.
Rely on me to mix up my whole spectrum. But that's a typical moment. But yep, essentially radio is one of those longer forms of light, and we discreetly discovered it in 1947. But an actually really cool fact is that we believe that the first time the light actually hit Earth was way back in 1667. But since we didn't have that powerful enough equipment to even capture it, we just never noted it.
Wow. I was just thinking about how this is a very stunning image. There's a lot going on here, but it was, so we discovered it in 1947 via radio, right? Is that what you said? So then we didn't really see anything. So this picture didn't come until much later as well. So just imagining the process of, oh, we're getting a weird radio signal. What does this mean? And now we got to figure out and point maybe a visual telescope there and go from there. Because I started looking through telescopes here at Ball State due to some of the astronomy classes, and we were looking at star clusters and nebulae, so I was expecting these beautiful vibrant colors in my telescope, and I look and all I see is kind of like someone spilled salt or pepper across the sky. It was very what's the word, foggy looking. It was just like a fuzzy object in my telescope, so I'm like, what's happening here? But
yeah, and you can see a lot of the what we call kind of filament structure within the nebula. And just as a reminder to everyone, when a massive star, like Kyree mentioned, reaches the end of its life, it goes through this process of dying. And ultimately, without getting too deep into the science, the core begins to collapse in on itself. And because it can't sustain itself and gravity begins to win and the rest of the star begins to fall in on that core and eventually bounce off. And you get these shock waves that carry out the outer layers of the star out into space. And these shock waves energize these particles and make them glow and light up. And so you see this kind of fog that expands out. And as you mentioned, Cassia is, I think, about 11,000 years old, if I remember correctly. So that makes it kind of a middle-aged supernova remnant. We'll talk about one, I think, here in a little bit that's much younger, about 1,000 years old. And you can really see the difference because over time, as the nebula expands out, the gas begins to become dimmer and dimmer. As the shock waves dissipate all of that material out into space, and it begins to fade away. But we're catching it at a really interesting time where you can still see these beautiful filaments that are surrounding where the core of the star had once been 11,000 years ago.
That's just wow.
That's super cool.
It's so cool. That, and if I remember correctly, so sometimes these remnants, right, because we're pushing layers out of the star, like you said, that also creates other heavier elements that we usually have here on Earth or that we find out in space. Supernovae kind of help create material that we otherwise wouldn't see because we need certain environments for that, whether that's temperature or more excited particles of some sort. So I heard that gold can be made from supernova remnants, like just either the act itself or just all of that gas and dust being pushed out at such a high speed.
It's amazing to think about. I believe the technical term is supernova nucleosynthesis, which is definitely a mouthful.
Yeah.
When you think about it, here on Earth, we have heavy metals, and we have lead and iron and all of these other heavy metal materials that are on Earth that we use in our daily lives. But where did those materials come from?
Right. Right.
They literally came from the cores of massive stars and the resulting explosions that begin to redistribute these heavier elements in the universe. Only hydrogen, helium, and a bit of lithium is what was originally created. And the rest of the elements beyond that were created in stars. And particularly, when you start talking about heavy elements and heavy metals, those had to be created through these events like supernovae. So we are literally made and surrounded by the stuff of stars, right? And it's sort of just this beautiful way that we exist today only because these old massive stars died millions or even billions of years ago.
Wow, it's wild. Sadly, I have to turn the atmosphere back on because we're going to move on to our next object. So how beautiful it is now, and then I turn the atmosphere back on. Can't even see anything. So we're going to zoom back
Honestly,
out.
can we just turn off the atmosphere? Like, don't worry about breathing. We'll worry about that later.
Oh, yeah. In real life, we can do that too. I'm just kidding. Don't do that. We love our atmosphere. Our atmosphere does a lot for us. So now we're going to move on to another high-energy astrophysics object. And this one in particular is very popular here at Ball State. I know a lot of my friends are studying this object for their research. So let's see. I believe Taurus is... So we're going to go back to our friend Orion. So we're going to go back to the south. Here on Constellation Crew, we love Orion, not only because Orion is just a really cool constellation and has a lot of fun stuff in it, it also helps us find other objects really, really well. So I'm going to zoom out here. I can already see where I need to go. Cool. And as a reminder, Stellarium is a planetarium type of software, which is great, and we love using it. It's very accurate for doing a lot of cool, fun stuff. But for the sake of our viewers, we love to tweak some things to make the sky look a little bit like what you would normally see out here in Muncie, where there's a lot of light pollution. So some of the stars look really big, or some of the planets look really big. I promise they don't look that big in the sky. They're pretty bright though, so that's why they're so big in the program here. But we're gonna go to Orion, so we're southwest-ish, and Orion's easy to pick out. So we have Orion's belt here, and then Orion's shoulders, and Orion's feet or knees, depending on how you draw him. But we're gonna go back to his belt. He's usually our pointing guide to things, and we're gonna use the belt to make a line to this pretty bright thing over here. This is a star. This might be, let me check. It is Aldebaran, as I suspected. It brought it up for me. Well, there's Taurus the Bull. I can get rid of this for now because I wanted to point out this V shape here. That's a really good indicator that you have found the object you are looking for, this V shape. And then you can go over and see this tiny little cluster here. That is the Pleiades. So if you found this little cluster, little dipper, as some people call it, and this V shape, you have found Taurus the Bull. But we're looking for a specific object called the crab. So let me type that in. There we go. Oh, I forgot. Stellarium's also a bit picky where I have to spell the whole thing. For someone who doesn't spell well, that's pretty difficult. The atmosphere is off. Wow. I love this one. This is a good image. It's always a surprise to see what Stellarium's images are of some of these objects, if it has an image. But this is the Crab Nebula, or M1. And for those who have watched Constellation Crew before, M1 or M anything, M with a number, is a part of the Messier catalog. And the Messier objects, or Messier catalog, was created by Charles Messier. I know his last name's Messier, that's the point. And he was a French astronomer who was looking for Halley's Comet, and he kept running into things that were not Halley's Comet. And he eventually got so annoyed that he decided to make a catalog of all of these things that were not comets. And M1, the first thing on his list, is the Crab Nebula, which I think is pretty cool. But remember, he was annoyed. That just blows my mind. Every time we bring him up, I always just find it very funny that most of the things that are on his list are actually really cool objects, where we're gonna run into another one later in this program that's actually really amazing. But it's fine, he really just loved comets. Everyone is entitled to like whatever they want in astronomy because there's a lot of objects. But
I always love that story that, I think the Messier catalog was the first one that was not created for science, but rather out of frustration.
yeah, that sounds about right. Absolutely.
And so that his fellow comet lovers would not be duped into things that were never actually comets. And I love that.
I mean, comets are really, really cool. Here at the planetarium, we were fortunate enough to get an amazing grant that gave us the opportunity to purchase some telescopes. And a while back, when we had that really awesome comet on the news, with the help of Caleb Wickham, who is a graduate student who works at the planetarium, and Bob Barrington came to help as well, we had a bunch of people coming over, and we were able to look at that comet. I forgot what its name was. I'm pretty sure it had a name. It was It was green. It was green.
It was green. Was it 73B?
Oh, it didn't have okay. So yes, the numbers and the letters are names. They're proper scientific names, but I'm talking like Halley's Comet kind of a name. But yeah. It was a green comet. I got to see it through that telescope, which was pretty cool. So comets are cool, but the Crab Nebula in particular, pretty cool. But its name is sort of, I don't want to say it's misleading per se, because when I think of a nebulae, it's just a collection of gas and dust that was kind of there, and it's like forming stars. In this case, the Crab Nebula is another supernova explosion, but it has something pretty interesting inside of this cloud of gas and dust that's being pushed away from the star on the inside. It's located about 6,500 light years away from Earth. So, but all of these little different colors are exactly like Dr. Millis was talking about way earlier when we were asking him some interview questions about how sometimes a star is so bright and so massive and powerful, it gives off certain types of light that can help excite the gas around it to different colors. So red is usually hydrogen gas that's been excited enough to emit into a visual light, usually red. Blue, I can't remember what blue is. Blue is usually a reflection going on. So when you look at the Pleiades, or if you come here to the planetarium often, we got some new window displays, and we have the Pleiades up and it's blue. It's because it's reflecting some of the light off of the gas and around, or more of the dust really, gas and dust around that star cluster. And it's easier for us to see blue, kind of like our sky, than it is for us to see red when it's reflecting something. So that's why sometimes things are blue. But I know that certain gases also are blue.
I think a lot of the crab is, and images like this are often false colored a little bit.
Yeah.
Just to show some of the different emission regions. I think a lot of particularly when you look at the edge and you see some of that red around the edge, that's actually from the outer layers of the stars that has been blown apart as it's expanding out. It's cooling off. And if we looked at this object with a radio telescope, you'd see this kind of ring of radio emission around the edge. And it's from that gas that's all kind of cooling as the nebula continues to expand. And as you kind of work your way in, you see more and more kind of different, and again, it depends the way that you color these images, but you'll see kind of different filament structures from different types of interactions happening.
Yeah. So in this case, the star in the middle is kind of a special star. So when stars die, there's a couple of things that can happen. In the case of our sun is going to expand and get really, really big all the way out to near Jupiter, and then it'll collapse again into a white dwarf. So a white dwarf is a very dense star, and they're not particularly bright, and they're not particularly big. Usually, I think our white dwarf is theorized to be around the size of Earth. I think it's gonna be pretty small compared to the sun now. And there's the white dwarf, and then there's of course a supernova explosion. I think sometimes don't stars just supernova explode and there's nothing after that, or is there always something after?
It's possible. In some cases, the core of the star can detonate, though I believe that's actually fairly rare. Usually we see one of two types of objects that are left behind.
Yeah, so then there's the white dwarf, and then in this case, this star is called a neutron star, which is very complicated. Trust me, we've been talking about it. But I believe it's called a neutron star because neutrons are very important in terms of like structure as a part of this star, and it's part of the material. But do you have a better way of explaining a neutron star, Dr. Millis?
Sure. So as you beautifully explained, when you have stars like our sun and they reach the end of their life, the outer layers of the star push out, they lose or they overcome gravity, and the core is left behind in an object that we call a white dwarf. And the reason we have these objects that are white dwarfs is that the atoms that make up the core are so packed together that they can't push together anymore. We have a fancy term for this called the electron degeneracy pressure. And all that really means is that we have the atoms with their nuclei and the electron clouds that are all pressed together really, really tightly.
Okay.
Well, in the case of a supernova explosion, the stars are much more massive, and the action of the core collapsing in on itself with all of that extra mass is pressing those atoms together, just like in the case of a star like ours. But the force is so great that it actually begins to destroy the structure of the atom itself. And those electrons are actually pushed into the nucleus of these atoms. The protons absorb those electrons, which turn them into neutrons. So instead of having a core comprised of atoms with protons, neutrons, and electrons all separately, everything combines together through a process called neutronization, and you're left with this structure, which is almost now entirely neutrons. And instead of having atoms where you have a core with a nucleus wide around it, it's all just nucleons, which means you lose all of that volume that used to be empty between the nucleus and the electron clouds. So you get all of these neutrons packed together as tightly as possible, and the structure of the object, of this neutron star, is now held together by this neutron degeneracy pressure, preventing it from collapsing even further. And then, of course, if we have a really massive star that explodes, the core may be so massive and the supernova event so intense, it could actually even overcome the neutron degeneracy pressure and collapse those neutrons down even further, and you end up with a black hole.
There you go. Thank you for covering that last bit. So supernova explosions can create a lot of cool and epic things, and a neutron star is pretty cool. And if I remember correctly, a lot of our homework assignments that we've done in the past when we were dealing with neutron stars, just to do some simple math. I promise it's simple math. But I think the average diameter of a neutron star is 10 kilometers, right? Mm-hmm. So just for the first time in a while, we can say a number that's actually like within my reference frame that I can picture, not 11,000 light years away, 10 kilometers across. It's actually not too bad. That's a very small star, in my opinion, compared to some other ones that I've heard.
Yeah, you think of these compact objects, like you said, the white dwarf, right? This sort of, and I tend to refer to these objects as stellar remnants, right? Because there's no more nuclear fusion happening, right?
Right.
When you think of a star, right? A star exists because it's in this equilibrium. There's all this energy created in the core pushing the object out, and the intense gravity trying to push it in, and it creates this equilibrium of that makes it a star. Well, now there's no more energy generated in the core. It's just collapsed down to an object that's hot, but over time will just cool, right?
Yeah.
And so they're really kind of stellar remnants. But you have like a white dwarf, which is the size of like a planet. And then you have a neutron star, which is about 6 miles across, right? 10 kilometers.
Oh, wow, 6 miles? Jeez, that's so tiny.
And then if I recall, wasn't the reason that a neutron star could also emit light was because of its insanely high rotational speed? I may be remembering that wrong, but...
Yeah, no, exactly right. They're incredibly dynamic objects. But think about all that mass, right? You had a massive star. Now, of course, the core was only a fraction of the total mass of the star that collapsed, but still, you're talking about a lot of mass, and it gets compacted into a volume that's 6 miles across, right? So The density that you're talking about is mind-boggling.
Yeah.
And I want you to play a little game with me, if you will.
Okay.
Imagine you had a 14-ounce can of soup, right?
Okay.
And somehow you're able to travel to the Crab Nebula and scoop up some of that Crab pulsar, neutron star, and fill your soup can with neutron star material. What do you suppose the mass of that soup can would be if it was filled with neutron star material?
Ooh, that's a good one.
Compare it to an object. Like, would that soup can be as massive as a person or an elephant, or what do you think?
I remember so on the Science Channel when I was a kid, that's all I would watch, and we would watch a show called How the Universe Works. And one of them is that if you went to a pulsar in general, and a pulsar is a type of star, which we can get into in another episode another time, but it's a very dense star, and if you went up to it and you got a teaspoon of it, that teaspoon would be Mount Everest weight. It would be like holding Mount Everest in a teaspoon.
Mm-hmm.
So I'm imagining the same thing for a can of soup, but maybe 2 Mount Everests now that it's a can of soup. That's my
guess.
I honestly, I want to debate probably even denser. I probably won't do Mount Everest. You know what? Why not? I'll be brave enough to even say the mass of our solar system.
I was about to. Yep.
Go big or go home. Go big or go home.
So I have 2 Mount Everests, and you have the mass of the solar system. Okay.
It's about in between. It's actually about the mass of our moon. So imagine taking the moon and cramming it into a can of soup. And that's about the density of these objects. And of course, now you have this thing that's so dense that it's the mass of the moon in a can of soup, but it's 6 miles across, and it's rotating hundreds of times per second. In some cases, up to 1,000 times per second. In the case of the crab, it's about 300 times a second.
Wow.
And they have extraordinarily powerful magnetic fields, these objects. And so you have this rapidly rotating, incredibly dense, powerful magnetic field wrapped around it. And it's literally driving material into the nebula. And this type of object that we're looking at here, like the crab, it's really 3 objects in one. You have the supernova remnant, the leftovers from the star, which is kind of the outer part. But then you also have the neutron star, or you mentioned earlier, Nicolette, a pulsar. And a pulsar is simply a neutron star that happens to be rotating very fast.
Okay.
So all pulsars are neutron stars. And in theory, we think all neutron stars are pulsars. We just may not always be able to measure the rotation. And then there's also something in between. This pulsar is rotating so rapidly and dumping so much energy into the nebula, it creates a type of object we call a pulsar wind nebula. Creative name. And if you look closely, in your image, you have that kind of square thing that's kind of outlining the center of the nebula. If you can push in there into that structure, you see what looks like kind of on the right edge of that, what looks like these kind of curved lines on the other side. Oh. Yeah, right there. And in. What you're actually seeing is the shock waves from the rotation of the pulsar pushing the gas outward. So if you took a bunch of images of the crab pulsar over a period of time and sort of animated them together, you would see what looked like ripples going out from that point. And it's because the pulsar is rotating so fast and it's driving that gas outward that you see these kind of ripples happen. And it's literally lighting up the nebula from the inside. And of course, over time, the pulsar is going to slow down. It's going to lose energy, and it's going to get weaker. And then eventually it'll become dim, and it won't be rotating anymore, or it will be rotating very, very slowly, and we won't be able to see it. But for now, because this is such a young system, only 1,000 years old or so, it is still very energetic. And so it's continuing to light up the inside of this nebula.
Wow. Well, somehow, Dr. Millis, you read my mind. I was going to ask at some point if there was any other side points you wanted to make about the crab, because I kind of had how far away it was and some general gist, but you pretty much covered it. The Crab Nebula could be its own episode on its own, to be honest with you. There's lots of things you could talk about it, but is there anything else?
It's one of my favorites. I have photos of it hung up in my office with different wavelengths. It's one of my favorite objects, so I know too much.
It is very, very fascinating.
It sounds really cool.
Well then, I'll open it up to both of you then. Do either of you have any final other points before we move on to our next object?
Nothing about this type of crab.
Okay, and thank you for that funny comment, because now we're going to go to a different one, unless John has something.
I do have something really just fun and silly about this.
Okay.
You know why it's called the Crab Nebula?
I always questioned it because it's not in a constellation that resembles a crab. So I was always wondered why. And then someone said it has something to do with a measurement of some sort, but that didn't make sense for me either.
Yeah, so the story goes, and I believe that this is true, the object was originally discovered in that it was first recorded and published that it had been seen in a telescope by a gentleman named the Earl of Rosse. And I always just loved his name, the Earl of Rosse.
Yeah.
Well, you know, this was hundreds of years ago, and so the telescope he was using was quite crude. And so when he found this nebula through his telescope, and he could see some of the filament structure, but not a clear picture of the whole thing, he thought these filaments looked like a crab. And so he referred to it as the Crab Nebula. And other people began looking at it. And then, of course, he later looked at it again through a more powerful telescope and kind of went, yeah, it doesn't really look like a crab, but because of that initial measurement and the name that he had associated with it, it stuck. And so we, to this day, continue calling it the Crab Nebula purely because of a poor observation by the Earl of Rosse.
I love that name now too. That's going to be stuck in my brain for the rest of the day. But that's standard astronomy stuff. A lot of my professors here at Ball State will always joke around and say, yeah, you don't like the name? Well, guess what? You can't change it. It's been the name for thousands of years. So that's very on par with astronomy. Well, thank you for sharing. That's actually very interesting. I always wondered why. Oh, gotta put the atmosphere back on. Boo. But at least it gives us air. All right, so we're gonna zoom back out and we have some other stuff to cover. So we're gonna move on to another type of crab. But now I gotta find it, man. Kyree, do you have any pointers on how to find it?
If I recall correctly, it should, what time is it now? It's 4:50? It's 4:50, huh?
Well, in Stellarium, it's about 10
Stellarium,
o'clock.
it's 4:50. That's a great question. I'd say like at about 12:55, maybe I could try to figure out where it is then. And at 12:55, it's like kind of westish. 12:55 tomorrow, I believe. Westish, kind of higher up in the sky.
Okay, we can try. All right. So Orion the Hunter is here. I'll zoom in just a little. And now that it's darker, it's actually a little bit more crowded.
Yeah.
But Orion is here. Let's see. I can't find my backwards question mark. Wherever my backwards question mark is.
I can't see the backwards question mark either.
Let's type it in. So spoiler alert for our viewers. I apologize, but it's easier to find it this way. We're going to be looking at Cancer the Crab. Oh, there you go. It was right there. Another thing that...
You just have to look further up.
Actually, it kind of does look like a crab. If you tilt this way, here's his
If you
body.
tilt this way,
and then he has little claws.
My biggest problem with the crab was that the renditions that I used to look at, so essentially if you look at this and just if you go a bit further up and like that diagonal line, the more diagonal line.
Oh, this one.
Yeah, that was never, no, up and
Okay.
more to you. That diagonal line was never shown in the renditions that I would look for Cancer. So it would just be this kind of straight line and then the two branches sticking out. And I was like, this looks like half of a Stickman. How is this a crab?
Yeah, that's the thing too about Stellarium. Its stick figures are very different than what I'm used to. One of the popular sky maps that we like to use here at the Planetarium is called Sky Maps, or skymaps.com. You can get them for free every month to print them, and they have the stick figures or the constellations in their most basic form, and usually they're very different. But it kind of looks like a crab here, which makes me sort of happy. We're going to get to a constellation that I firmly disagree with in a little bit. But anything cool about Cancer the Crab?
Well, as some of you may know, Cancer the Crab is one of our 12 zodiac constellations. It's the reason I like this zodiac so much is totally biased, but I am actually of the Cancer zodiac sign. I was born the day after the region it starts, the time region it starts, so that's why it's my favorite, because it's me.
Just made it, just barely made it.
Just barely made it. And essentially it's called Cancer because it stems from the Latin word which means crab, so that's why it is the crab constellation, because Cancer in Latin or something like that should equal crab.
Should equal crab. Cool.
Should equal crab. And based off of how I used to saw the renditions without that extra like line poking out of the long line, I just thought of the really long line as the body and then the two branches as the claws, and then I was like, okay, fine, I guess it looks like a crab. But it's been a big gripe with me for a while. Personally, my favorite thing about it is, again, if we mentioned to what I was talking about earlier about how all the stars are objects within a constellation are given a name, and then before it's given a Greek letter to indicate how bright it is, with alpha being the brightest and going down further. My favorite one is actually Delta Cancri, because it's an orange giant star, and essentially it's a star that's basically left its main phase or middle age of its life, which we like to denote as the main sequence, and now it's essentially cooling and becoming an orange giant, and that's why I kind of like it. Also, its common name, forgive me if I mispronounce it, Aeschylus australis.
Oh, I just clicked on that.
Yep.
There we go. Let's see.
It means southern donkey colt.
Wait, what? Wait. Wait.
In some definitions, it's also called southern donkey, but it literally means southern donkey colt, which I find hilarious.
Thank you for saying it again, because I really thought I misheard you. Astronomy, man, like just, oh my goodness. I'm gonna see, usually you can't do this in Stellarium, but, oh, is that atmosphere off? Now it is. Darn, it's just a point of light.
Unfortunate.
I thought maybe it would be. We did see something cool, I'm not sure what this is, but hello.
Hello.
Welcome, you must be a star cluster of some sort. But we'll zoom back out. So there you go, Cancer the Crab. We don't cover Cancer the Crab often. That's why it was really brief.
I think one of the biggest reasons why we don't cover it is because, one, it barely looks like a crab, and two, I believe it's actually the second dimmest constellation in terms of the zodiac. I don't remember what the most dimmest is, though.
Yeah, so zodiac constellations are very, very popular here at the Planetarium, and I can totally understand why. Astrology is very, very big, especially with younger audiences. So it's very intriguing and fun, but sadly, a lot of the constellations are pretty dim, and they're really hard to find or really hard to see. So I'm a Capricorn. So Capricornus is a winter constellation, so it's sort of going out of the sky now-ish since we're heading into spring. Or spring.
Yep.
Yeah. Winter,
Yes,
spring.
spring.
Yeah, okay. Jeez, I gotta go back to elementary school, guys. Remember the song. So we're going into spring now, so it's getting lower in the sky, but it looks like a scone to me, if you've ever seen a scone. It's not a very sharp triangle, it's like a puffy triangle. But it's so hard to see. It is so hard to see, especially here in Muncie, where if you're on campus, there's lights everywhere, which I greatly appreciate, because when I walk home in the dark, I love some light. But now I can't see most of the constellations I want to see.
Exactly.
But is that all we have for Cancer the Crab?
That's all I have for Cancer.
Okay. Now it's
Southern
my
donkey
turn.
colt.
Oh gosh, I just can't get over that. So I'm actually gonna go back in time a little bit to make it just little bit brighter. Whee! Or get the sun up just a little bit, because all of these amazing stars are beautiful. And if you were to go to a very, very dark location, you would be able to see almost all of these lights and even a faint band of the Milky Way. But that's really hard to find, and that's not what our sky typically looks like here in Muncie. So, our good old friend Orion, and now I gotta look for a particular shape. I gotta find it. So what we're looking for is a backwards question mark, and I'm going to ask my crew members if they can see it before I do, which might be a little difficult.
It might be, but it's the backwards question mark should be really close in proximity to
Yeah,
Cancer.
so it's sort of by Orion typically.
Yep.
And Cancer the Crab was up here, so we just gotta follow the. Oh, there we go. I found it. So I moved it. Yep. See, process of elimination once you find it again. So it's more in the southeast, so we're gonna actually just above directly the southeast. So as we say in the planetarium, just put on your fancy cardinal points on in the sky. Just get your handy dandy remote and put them on, as one does. And once you see southeast, you'll go straight up. Or if you use Orion, you can use this very bright star, Betelgeuse, as your reference point and kind of just draw a line in the sky all the way across, going from southwest to southeast until you see a backwards question mark, which is right here. And I'm gonna, yes, see, ooh, see, Leo the Lion and I have some issues. So this is Leo the Lion, Leo the constellation, the zodiac constellation, and it's a wonderful constellation. It has a wonderful myth. Usually it's associated with Hercules, and if you've seen the Disney adaptation, which is not entirely accurate in terms of the myth, but it's always fun, you'll see Scar from The Lion King as his lion mane coat, and that's kind of the myth, is that this lion is very special and particular, and it's really, really hard to kill by man-made objects, typically, so swords and arrows and things. And it had a very specific name. I think its name was Nemean, 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 maybe. I'm not pronouncing that correctly, but it's basically cannot be pierced by any weapon, and that's why Hercules wanted it. It was one of his challenges, I believe, and because it's a really awesome thing to wear when you're a warrior and fighting monsters and stuff. But to me, that doesn't look like a lion. See, Orion makes sense. It kind of has like his belt, right? And his sword and his feet or knees and all of that. That looks like a mouse. There's his tail. And then there's his cute little nose. His little body. It looks like one of those cute little mouse hamster things that you would get as a kid. What were they called? Zoomies? I used to have them. And they were little hamsters that would run around on a track. Or like the remote mouse that you would use to scare your mom. Or I would scare my mom, because she doesn't like mice. But it looks like a mouse. But everyone says that this is how it's supposed to be looked at, is that this is his head, his lion's head and mane. And then he's laying down. He or she is laying down. And there's his mane. But I don't see that, man. I really don't.
I will be truthful. I kind of saw the lion before I even thought of a mouse. It just never clicked in my head, but now I see it now that you explained it.
Now that you have shown us the mouse, I can't unsee it.
I can't unsee it, yep.
I always saw the mouse, because I guess I'm very literal.
I was like, yeah, I can see how that's a lion, and now I'm like, nope, all I see is a mouse.
Welcome to my club.
It's not. And then it like just makes it worse because like the tail is on the mouse's back instead of towards the rear.
It's a curling tail. You know, mice have curly tails, usually, sort of. But yeah, it's just one of those funny things that I always have, because I was really bad at those images. When I was younger, a lot of the kids liked getting those images where you could see multiple things in the same image. So you either saw a woman or a rabbit or a vase or whatever you were supposed to see. There's multiple objects you could see. And I always saw the one that no one else could see. There was usually like 3 objects or 4 or something, and I always saw the one that no one saw. And I'm like, how do you not see it? It's right there. Or maybe Kyree would remember this. Do you remember the golden white or black and blue?
Oh no! For funsies, what did you see?
I always saw golden white. Oh no!
Okay.
Oh no! Are you familiar with this? Oh, it was old.
I'm with you. I saw the golden white.
How did y'all see the golden white?
You know what? I have the head of the department on my side, so it's golden white, guys. End of debate. I feel bad for Kyree. I'm sorry.
Or if you team with your favorite Constellation Crew member, which is obviously me, it's blue and black.
You know, we could get a poll and you'll be very disappointed, but we're not gonna go there.
We could get a poll.
That aside, we have one more really cool object that I think we really should cover before we have to start ending our program today. And it's very popular because it's been in the news as of the past couple of years, and everyone asks for it now because before you couldn't even ask for an image of this object at all. It was very mysterious. It started as science fiction to reality, but we have no picture, to now we have a picture. So let's see. I'm actually going to type it in. So it's another Messier object. Yay. So again, he said that Messier didn't want to see these objects because he wanted to look at comets. Ooh, I wonder what constellation this is.
Yep.
Let me let's go up. Wow, it looks like the Earth is moving instead of the sky. Oh, I think this is...
It's Virgo.
Oh, it is Virgo? Okay.
Yep.
Thank you. Well, yeah, this is your object, Kyree. So let's see, do we have one? Does Stellarium have one? It does not.
I think you moved.
No.
No, you didn't move. No, you didn't
Yeah.
move. No, you didn't. You moved the time, that's why.
Well, I think we will provide our viewers with an image at some point, but for now we can just look at this really awesome constellation. So what is M87, Kyree?
All right, so M87 is actually what we believe to. Oh, not what we believe. It's a galaxy. It's another galaxy, and the cool thing about it is that it's a really, really massive galaxy, and is one of our most massive galaxies in our local universe, and the second most massive galaxy within the Virgo region, if I recall that correctly. And I guess we can do a bit of pot shots here. How much larger in terms of diameter, so like give a percent, do you think M87 is in comparison to our Milky Way?
So like
Go ahead.
How much larger in diameter? So like 20% larger, 80% larger, 70% larger, 250% larger.
I'm gonna put all my eggs in one basket, 90%.
I'm going to say 50% larger.
You are actually almost perfectly on the dot, Dr. Millis. It is 51% larger than the Milky Way
Darn
galaxy. And that's really, really insane. If we talk in terms of mass, it could even potentially be 200 times the mass of the Milky Way, which is, it's just super cool to just think about galaxies that are just like exponentially more massive than our own. And of course, to give us another perspective of how far away it is, if we remember how Cas A was 11,000 light years, or about 64 quadrillion miles. Yeah, M87 is 53 million light years away.
53
So
million.
if 1100 was just 64 quadrillion miles, I don't want to think how far away 53 million light years is. But you can go ahead and try to imagine that. But I think that's too.
Hear about that? Remember, is that 50 million light years away is local.
Right.
Yes.
To give you a
The
sense,
fact that it's local makes it even worse.
something 50 million light years away we consider local to us, right? That's amazing.
It's really mind-boggling. Like, oh
Yeah.
man.
Yeah, you could
Harder
be.
to even think of farther beyond, and that's just considered local. It's really cool how much we have here. It really is. And another fun thing that we have slightly mentioned before, while we were just scrolling through Stellarium. If you were here on previous episodes, you would be familiar with the term globular clusters. Essentially, these are large groupings of stars that are essentially bound together by gravity. And what I think one of my favorite things about this is because us in the Milky Way, we have about like 150 to 200 globular clusters. Is that about correct? M87 has 1,500. So 15,000. I mean, not 1,500, 15,000. That's it. It's really cool just what's out here.
Wow. So M87 also has a particular strong meaning for me in terms of the black hole image, right? This is the black hole image, right? M87 is the same one?
Mm-hmm.
Okay. Because I also saw recently from our Planetarium director, Dana, she showed this to me. So it is theorized that most galaxies have a black hole in the middle. But it's a theory. It's not confirmed because we know we have one. Sagittarius A star, and Sagittarius A star can fit inside of M87 comfortably. So it's not like on the brim or anything. It's just in there. And this M87 is huge. So we say we have a supermassive black hole. I think M87 is the actual definition of a supermassive black hole. It's huge.
Yeah, we talk about Sagittarius A star, and it's about 4.5 million times the mass of our sun, which in itself is mind-boggling. 4 million suns packed into this tiny object that we call a black hole that has a pretty extreme reach. You look at M87, and it's not 4 million or 40 million or 400 million, but rather about 2.5 billion times the mass of our sun.
Yep. It's
wow. I can't. These numbers are big.
These
some big numbers. I can't. That's the definition of a supermassive black hole to me.
Yep.
I know there's like, I don't want to say baby ones, because black holes are pretty big in general. They're pretty big objects. But just, after seeing that image, I was like, oh yeah, we have a supermassive black hole, aren't we cool? Never mind. Never mind. Yeah. But M87 is a particularly interesting object, but it is one of our first and so far only, as far as I know, image of a black hole that we have. And we were mainly able to obtain it because there's two types of black holes. There's, sort of. There's two types of black holes that I know of, as far as I know. There's active ones, and then there's non-active ones. And active ones have material being sucked into it, so stars, gas, dust, and it's all being ignited or illuminated. It's becoming bright because it's rapidly spinning around it, going into the black hole. And that's why we're able to get images of M87 like this, because it's an active black hole. So we're actually seeing the stars and the light being warped and sucked into the black hole, where inactive ones, they're just roaming around the galaxy with no companion. So we can't see those because they have nothing illuminating around them per se. But that's why this is one of those like rare occasions of like, the reason why we got it is because it's actively taking in material and we're seeing that material be lit up from that.
Yeah, if you survey all of the galaxies that we know or strongly suspect have supermassive black holes, only about 10% of them are active, and they tend to coincide with the most massive, not always, but typically the higher end of the more massive galaxies in the universe. And it's, as you said, something is triggering these black holes to be active. It's consuming material in some way, and this material gets pulled in around the black hole in what's called an accretion disk. Yeah. And it's this material, and it's being compressed. So because of the black hole pulling the material in, the material is causing friction, and it's being pushed into other material. And as we talked about earlier, when you start interjecting energy into a system, and compressing it and heating it, it begins to glow. And so you can actually see this glowing disk around the black hole. So the black hole is the absence of light. We don't see anything, but we see this glowing disk heating around this central point. And we can begin to measure the mass of that object, of that black hole, simply because of how it's influencing all of that matter around it. And that's one of the ways that we know that it is, in fact, so big.
Wow.
And we see this, like I said, we see this in a lot of galaxies, these supermassive black holes that also have incredibly powerful magnetic fields. So some of that plasma, that heated plasma in the accretion disk, as it gets pulled towards the black hole, can be swept up in the magnetic field and shot out in these jets of energy. And you may have seen some images of M87 where you see this very distinct jet of what just looks like a ribbon of glowing gas coming out from the elliptical galaxy. And that's the jet of material that's being shot, not directly at us, but sort of in our general direction. And we can see this sort of filament of gas coming out.
Wow. It's a very stunning and beautiful image itself, and then the object itself is also very, very fascinating.
Yeah.
But that is our final astrophysics object. So now we're into the part of our program where we get to ask some more questions for Dr. John Millis. I'm very excited. So I'm going to go back to our Orion constellation really quick. Our good old reliable. No copyright, please, Nickelodeon. I promise. Only SpongeBob fans will get that joke. But so before we move on to any of the questions, do either Dr. Millis or Kyree have any final comments on any astronomy objects before we conclude?
Take a look at M87.
Yeah. Well, you can't see it through a telescope. Sorry.
No.
Take a look on the internet.
Simply just go there.
Oh, yeah, absolutely. You know, just get in your rocket ship. We all have one nowadays. You know, we're in the future. We should be having floating cars by now.
If you have a good enough telescope, you should be able to see M87 as the galaxy, but you won't see the black hole.
Yeah, I was going to say, unless you have the telescope that was used to get the image, which is literally the size of the Earth, which is another fun topic we can get into another time. But mini Q&A session. So these are mostly my questions that I have for you, Dr. Millis. So the first one is, and we kind of covered it already, so if you either want to change your answer or go in more detail, that's also fine. What's your favorite astronomical object and why?
I mean, I have to go with the crab. I mean, the Crab Nebula.
Yeah, understandable.
You know, there's not much more I can say about it. I could try to come up with something different, but I mean, yeah, it's just my favorite.
Yeah, we can just tell our viewers to go back in the beginning of the episode and check out the Crab Nebula, because you did a fabulous job of explaining all the cool aspects about it. So
it was really cool.
Awesome. So my next question for you then is, what would you say to either younger you, or if you don't want to be too personal, you can pick a young viewer watching our episode today. What would you say to them about getting into the astronomy field?
So I would say several things. Number one, really pay attention in your math and science classes.
Yes.
Because a lot of doing science is learning how to ask good questions and learning how to think deeply and critically about material as you are learning it, and to really dive deep into the science of what's happening. And math is the language of science, and you have to be able to be comfortable with math, but also use math as a tool in order to say things about the objects that you are studying. So those I would definitely say, but also just be curious, right? If you're interested in astronomy, ask questions, go to planetariums, go to online broadcasts about science like Constellation Crew, and absorb this material. And when you have the opportunity to talk to scientists, to talk to people presenting at planetariums, ask them questions. And we love to talk about this stuff, so we welcome it.
Yes, exactly. And I would like to preface that math is very, very important, and I love math. But I will admit that don't get discouraged if your grade doesn't reflect what you think it should be in your math class. If you can sit down in your own personal bubble, like at your desk at home or something, and be able to solve that math problem in your own time on your own terms, in my opinion, that's good enough. So don't be discouraged by that. I feel that sometimes people put this time restraint on math so that you can solve it quickly, which is a useful skill, absolutely. Being able to add, subtract, multiply, and divide big or small numbers really quickly is important. Doing simple algebra expressions can be useful to do on the fly, or Bob talks about doing estimates and summations rather quickly. That's also very useful. But don't be discouraged if you're getting a C in math and you can't understand why, but you can pinpoint that it's more of a time issue. Because what you see on TV sometimes is the case where theoretical physicists and astronomers do have a lot of time, in a way, to figure out some of these math problems and work it out. So don't be discouraged if it's a little scary.
Yeah, I mean, I'm not a mathematician. You don't have to be a mathematician, right? But you have to be comfortable. I think that's one of the biggest things that holds students back, is they are afraid of the math. And you don't need to be afraid, right? Math is a beautiful piece of the universe, right? So many things that we experience on a daily basis tie back to mathematics. And, it's a friend of mine used to teach a class called The Beauty of Math. And I never took the class, but I was always intrigued by that class, that he really wanted to demystify what mathematics was and to show students that it can be beautiful and it can be interesting and not something to be afraid of. And so even though you may not feel like you have the most natural skill, like Nicolette was saying, and you maybe can't solve the math problems the most quickly, that's okay. That's not what the measure is. The measure is, can you appreciate the math? Can you use the math when you need to? And to just not be afraid of it.
Exactly. All right, we have two more. One is a Kyree-inspired question. Kyree wrote this one himself. It's, what is one thing you wish you knew before joining the astronomy field?
Okay, I have two things.
Okay.
One, this is kind of just a fun backstory, but when I was growing up, I was good at math and science, and neither of my parents came from STEM fields in their education. And so when I said I liked math and science and that's where my strengths were, they said, well, you should be an engineer, right? Because that's what everyone should do if you're in math and science, right? And so I was like, okay, well, I guess I'll go to college to do engineering. And then in high school, I had a chance to take some physics classes and some engineering classes. And I found that I was really fascinated by the physics, and the engineering. I just felt like I was sitting in front of a computer all day, just staring at screens and doing like CAD work. And I was like, I don't want to sit in front of a computer. I want to do the science. And so that's why I ended up going into physics and then ultimately astrophysics. Where, by the way, for my research, I sit in front of a computer all day. So that's one thing, is be realistic about what astronomers actually do. And again, just for the particular field that I went into, it's very computational. So even though that is what had initially turned me off the engineering in high school, was the prospect of sitting in front of a computer all day, I ended up sort of doing it anyway. But the other side of it is that sometimes it does require you to stay up all night to take data. And it's something that sort of sounds obvious, but you don't really think about until you get into doing research and you're like, oh, I have to take the data and it has to be dark outside. So, okay, I guess I'm staying up all night to do that. And so those are, but you don't always have to, right? I'm actually getting ready to go on shift for the Veritas Array in Southern Arizona. So I'll be working nights for a couple of weeks taking data. But it is fun and it is exciting, particularly if you see something unexpected, which happens more often than you would think. And so there is some excitement around it because you're taking cool scientific data using a really cool instrument to do it. And then, like I said, sometimes while you're taking data, you see something you didn't expect, and that just really energizes you. So.
I remember a science teacher telling me this one joke because they liked astronomy a lot. And they were like, essentially, while you're taking data, what it's like is just you're sitting there all night just taking data, and then one thing doesn't look right or one thing you don't expect, and then the whole room goes wild.
Yeah, it sounds about right. I remember I started binary star research with Dr. Todd Vaccaro, another professor here at Ball State, and he gave me some of the data to do some work with. So I had to plot it first because this is when I first started. So I just got into it. So he just wanted to get me used to some software and just had me plot a light curve. And the light curve was upside down. Typically a light curve it's a dip, so it's going in a straight line and then it goes down. And then it comes back up, and then it goes in a straight line again. This one went up, and then down, and then a straight line again. And I whip around, and I said, I think I broke it. I don't know what happened. Everything's fine. Everything's where it's supposed to be, and I'm freaking out. And he's like, Nicolette, calm down. It's just a flare. We caught a flare instead of a light curve. It's fine. But I'm freaking out thinking I broke his data. I did something wrong because, again, I just got into it. And he's like, don't worry, it's a flare, which is actually kind of cool because you don't see flares often with binary systems, but there you go. I was so scared. All right.
If you were a part of our structural geology class, I think you would affectionately refer that to as an anti-climb, an anti-syncline.
See, now you're just going to make Heidi upset. We have one more question. And it's inspired by our Planetarium director, Dana Thompson. We have, how do you stay motivated in your field?
That's a really great question, because sometimes you can get overwhelmed with the work, right? The day to day. And particularly as a department head, I write a lot of reports and I, have to respond to lots of emails, and it can get kind of tedious. There's a lot of it that I enjoy doing the administrative work, but there is a lot of stuff that just sort of feels like you're just keeping busy, having to just do all the day to day. But then I have the opportunity to work with students. And this is through teaching classes. I teach a wide range of classes here at Ball State, from introduction to astronomy for non-science majors up to, a graduate course in quantum physics or something like that. And I love the breadth of courses that I get to teach here, and just see students learn and really kind of see those light bulbs go off is just energizing to me. But also having students come up and ask questions, and it's sort of the awe and wonder of, wait, the black hole's 2.4 billion times and they can't get their mind around it, right? And they just want to talk about it and learn more and try to understand it. And it gets me excited all over again for learning and talking about these sorts of things. And then the other piece of it is, when we do get to make those breakthroughs, they don't happen very often, but sometimes you're studying something and you realize, oh my gosh, this is something new, and it just sort of motivates you to keep going and keep going forward. And so I think it's just the excitement around just doing the work, and the breakthroughs that can happen. And then also just, like I said, working with students and having those interactions of not just the act of teaching, but having conversations and getting excited about the material all over again.
Wow. Yeah, that's pretty much how it is here at the Planetarium. I fully agree. But I know that Dr. Millis has a lot of stuff that he has to do today. He is the department head and he is doing research. So we have to cut this episode short, or long, if only you knew. But we thank you so much for all of you coming to watch our episode today. And thank you, Dr. John Millis, for coming on as a guest speaker today.
Thanks for having me. I thoroughly enjoyed it. And maybe I'll come back again someday.
Yeah, that would be great.
That would be
great.
amazing.
So, of course, we encourage you to check out any of our social media platforms here for the Charles W. Brown Planetarium. And we also encourage you to come in and do exactly what Dr. Millis talked about. Come in, talk to us, ask questions. We do have wonderful activities before every show, and they're there for you and your viewing pleasure. So please come in, ask questions. We love talking to you all, and we love seeing you here on Fridays and Saturdays. And we also have some new shows for this weekend. So feel free to come in and check them out. And thank you all again for coming. Bye, everyone.